self-improving language models with Bidirectional Evolutionary Search by Guowei Zhu and a team of researchers from Harvard and MIT.
Right.
So look, right now the entire AI industry is banking on test-time compute to build smarter reasoning agents.
Oh, absolutely.
We operate on this fundamental assumption that if we just give models more time to, think like, if we let them generate thousands of possible answers before picking the best one, they will eventually find the correct solution.
Right. That's the whole bet with scaling inference compute.
Yeah, exactly. But this paper mathematically proves that assumption is totally flawed.
Yeah.
Like if a model is stuck inside its own entropy shell, giving it more inference time just means generating slightly different flavors of the exact same mistake.
Yeah, and it's a massive paradigm shift for anyone working on reinforcement learning with verifiable rewards or RLVR.
Because right now the standard approach is just hit a wall, right?
Exactly. I mean, currently, if you want to scale up post-training or inference compute, you are probably relying on best of n sampling or some tree search method like tree GRPO. But those methods fail on genuinely complex reasoning tasks because they rely exclusively on autoregressive expansion. They build candidates one token or, one step at a time.
It's blindly walking forward.
Exactly. And the authors prove that this step-by-step expansion mathematically confines the search to a very narrow probability distribution.
It's the entropy shell.
Right. So bidirectional evolutionary search, or BES, breaks the model out of that trap using two coupled mechanisms. First, a forward search that applies biological evolution operators.
Like a crossover and mutation, right?
Yeah, to recombine different reasoning trajectories. And second, a backward search that recursively decomposes the main goal into a tree of sub-goals. That provides really dense reward signals so that evolution isn't just, flying blind.
Which is huge. I mean, if you are an ML engineer tuning an agent right now, you know this pain perfectly.
Oh, absolutely. It's the worst.
Your model gets like 90% of the way to the right answer, fumbles the final API call or some basic math operation, and your pipeline scores the entire 1,000-token reasoning chain as a 0.
It's incredibly frustrating to watch.
It really is. So to understand how BES solves this and practically stops reward hacking in its tracks with honestly minimal compute overhead, we first have to dissect this entropy shell concept.
Yeah, we need to look at why generating candidates autoregressively creates that invisible wall at the frontier of a model's capability.
Exactly.
So think about how we construct those candidates in best of n sampling or, say, Monte Carlo tree search. You start with a prompt, and the model predicts the next token based on the highest probability.
Right, just standard next token prediction.
Then it takes that token, appends it to the prompt, and predicts the next one. Every single step relies entirely on the conditional probability of the step immediately preceding it.
It's locked in.
Yeah, and the theoretical proof in this paper shows that this expansion-only search is mathematically confined to what information theorists call a typical set.
Okay, typical set.
Right, and the size of this set is proportional to the exponential of the trajectory level entropy.
So, e to the power of ht, where ht is the total entropy or uncertainty of the generated path.
Yes, exactly. Now, for simple tasks, the correct answer usually lives comfortably inside that typical set. The model's existing beliefs generally align with reality.
Sure, for basic stuff.
But for highly complex math problems or intricate multi-step coding challenges, the actual correct solution is often highly specific and deeply counterintuitive to the base model.
It's outside its comfort zone.
Exactly. The correct reasoning path lies in a low probability region far outside this entropy shell. It's in a region of the probability space that the model basically doesn't believe exists.
Man. And the researchers draw a really fascinating biological parallel here to illustrate why current test time scaling fails at that point.
The asexual reproduction analogy, right?
Yeah, exactly. Expanding a single reasoning trajectory, which is like the bedrock of our current state-of-the-art inference, is essentially asexual reproduction.
Right.
Every offspring, every new candidate generated in a bean search or a Monte Carlo tree is just a direct linear extension of a single parent.
Which is incredibly limiting.
It is, because if your model generates two completely independent reasoning paths, and both of them stumble upon a brilliant beneficial mutation in their logic, they can never combine those strengths.
Because in asexual reproduction, you are basically waiting for lightning to strike twice in the exact same lineage.
Right.
And translating that back to an ML pipeline, it tells us exactly why scaling up n in best of n sampling only yields linear improvements in coverage.
Because you're just pulling more of the same.
Exactly. You are just drawing more independent trajectories from the same isolated policy.
Yeah.
If the optimal trajectory requires multiple rare insights, and it's hiding in a region with a tiny policy mass, cranking n up by a factor of 10 or 100 is just a hopelessly inefficient way to find it.
You are forcing the model to independently hallucinate a miracle on a single branch.
Perfectly said.
Which means we need chromosomal recombination for LLM reasoning traces. We need a mechanism for, well, sexual reproduction between different thought processes.
Right, which brings us to the forward search component of bidirectional evolutionary search.
Yes. Since autoregressive expansion is trapped in the entropy shell, the researchers introduce 4 specific evolution operators to smash through that boundary.
Yeah, these are direct edits applied to the sequence of steps in the model's reasoning pool.
So let's walk through how these actually alter the probability mass.
Yeah.
The first operator is combination.
Combination is incredibly straightforward, but really powerful. You take 2 trajectories that share a common prefix.
Like maybe they both started with the correct initial algebraic setup.
Exactly, but then they diverge down completely different logical paths. Combination merges them by concatenating their distinct suffixes together into one single extended candidate.
Oh, so the model basically says you both had interesting ideas after step 3, so let's try executing both strategies sequentially.
Exactly.
And then you have deletion, which feels like the natural counterweight to combination.
Yeah, dilution simply removes a weak or incorrect interior step to condense the response.
Because models ramble all the time.
They do. If you think about agentic workflows, models frequently hallucinate intermediate steps. They might write a script, realize it failed, write a correction, and then move on.
Right.
Deletion acts as a pruning mechanism. It strips out the hallucinated detour, stitching the valid premise directly to the valid conclusion.
Which just drastically increases the efficiency of the reasoning trace.
Right.
Now, those two make intuitive sense for cleaning up a single branch. But translocation and crossover are where things get really wild.
Oh, definitely.
Because translocation involves taking a single isolated reasoning step from one path and transplanting it directly into the middle of another path.
Yeah.
And crossover involves slicing the prefix of one trajectory and fusing it to the tail end of a completely different trajectory.
Right. True recombination.
But wait, I have to push back here. If we were just like blindly slicing and splicing reasoning steps, or worse, lines of executable Python code, aren't we going to just generate broken garbage most of the time?
Well, yeah, you would.
I mean, dropping a random variable assignment from path B into the middle of a loop in path A is a guaranteed syntax error.
Oh, for sure. But the implementation details prevent exactly that kind of chaos.
Okay, how?
So for purely text-based logical reasoning, the researchers found that direct string concatenation at the paragraph boundary actually works surprisingly well. LLMs are robust enough to parse a sudden shift in textual logic.
Okay, fair enough for text.
But you were completely correct about executable code. In the open problem benchmarks they ran, which output raw Python, you cannot rely on simple string concatenation.
Right, it would just crash.
Exactly. So for those domains, BES uses the LLM itself as a semantic compiler. It uses a prompting mechanism to actually perform the evolution operators.
Oh, wow. So the system explicitly prompts the base model, like here is program A and here's program B, extracts the core algorithmic trick from B, translocate it into A, and ensure the final output is structurally valid.
Yeah, syntactically correct and everything. By doing it semantically, you enforce structural validity while still transferring the genetic material of the idea.
That's incredibly clever.
It is, but, I mean, your broader point remains true. Even with semantic translation, most mutations generated by crossover or translocation will be failures.
Right, they'll just lead to dead ends.
And that is perfectly fine, because in evolutionary biology, the vast majority of mutations do not result in a fitter organism. What matters is the generation of diverse candidates that exist outside the original probability distribution.
Which the paper actually proves mathematically, right?
Yes.
Multi-way block evolution results in expected log probabilities that lie strictly beyond the entropy shell boundary.
Exactly.
The expected surprise of a recombined sample actually exceeds the normal trajectory level entropy by a factor they call the block total correlation.
Which means the search is mathematically forced to explore genuinely new spaces. Because the search space of possible reasoning steps is so vast, you only need a tiny fraction of these recombined trajectories to actually be improvement.
It's just a volume game at that point.
Totally.
All right.
By constantly combining fragments of partial success, The search algorithm makes massive, nonlinear progress that simple autoregressive decoding could just never achieve.
But wait, generating these wild, out-of-distribution mutant trajectories introduces a huge blind spot, doesn't it?
How so?
Well, if our verifier only looks at the final answer of a 1,000-token chain, it's going to throw away a brilliant mutation just because it made a tiny math error at the very end.
Ah, yes, the sparse verification signals problem.
Right. Because if a mutant trajectory gets 99% of the way to the correct answer, but fails the terminal evaluation, standard search frameworks just score it a 0 and discard it.
Which is exactly why we can't evaluate just the finish line. We have to grade the intermediate steps. And that is why they coupled the forward evolution with a backward search. The model is prompted to recursively decompose the top-level goal into a tree of fine-grained, verifiable sub-goals.
Oh, so it builds a rubric for itself.
Exactly. It provides the dense, intermediate feedback required to identify which pieces of a failed trajectory are actually valuable.
Let's translate the math on why this decomposition is so critical for everyone listening. The paper notes that relying on terminal-only search means your required sample size scales multiplicatively.
Right. So let's define the variables to make this concrete. Let P be your model's probability of successfully completing any single reasoning step.
Okay.
And let M be the total number of steps required to solve the problem. If you only verify at the very end, you have to get every single step right in sequence on a single try.
Which is brutal.
It is. Your sample complexity, the number of rollouts you need to find one correct answer, scales to big O of P to the negative M. Yeah, if P is 10% and you need 10 steps, you are looking at 0.1 to the power of 10. The chances of success just plummet exponentially. You are essentially asking the model to get lucky 10 times in a row.
But the backward-guided bidirectional search fundamentally alters that math.
Yes, it does.
Because the backward search tracks and banks completed sub-goals. It reduces the sample complexity from an exponential nightmare down to big O of P to the negative 1 times the log of M over delta.
Exactly. It turns a multiplicative hitting problem into an additive sub-goal collection problem.
Right. You don't need one perfect run. You just need to collect the pieces across different runs, and the evolution operators will stitch them together.
To really visualize this, look at the multi-hop question answering case study from the music dataset in the paper.
Oh, the James Blunt one.
Yes. So the model is given a really complex query. What is the record label of the artist who originally recorded Back to Bedlam?
Right. And as humans, we know we have to break that down. And the backward search does exactly that, generating a sub-goal tree. So, goal 1, identify the artist who recorded Back to Bedlam. Goal 2, identify the record label of that specific artist. Now, the forward search kicks off. Branch A starts searching Wikipedia and confidently concludes the label is Atlantic Records.
But that's the incorrect final answer. So under a standard paradigm, it just gets a 0 at the terminal node.
Right, because it missed the nuance of the original release.
Yeah.
Meanwhile, Branch B takes a completely different route. It researches the entirety of James Blunt's career.
It pulls in massive amounts of context.
Exactly. And it discovers that both Custard Records and Atlantic Records were involved in his early career. But Branch B gets overwhelmed by the context window and also fails to generate the exact correct final answer.
So under standard GRPO or Monte Carlo tree search, both Branch A and Branch B are scored 0 and deleted. They failed the final check.
Poof, gone.
Right. But under BES, the system evaluates them against the sub-goal tree. Both branches successfully achieved goal 1, right? They identified James Blunt. And Branch B also successfully identified the Custard Records connection, even if it fumbled the final formatting. So both branches receive a partial reward score of 0.3 for hitting those intermediate sub-goals.
And because they have high sub-goal scores, the forward search preserves them in the population pool and selects them as parents for evolution.
Exactly.
And then the translocation operator steps in. It takes the specific, nuanced reasoning step about Custard Records from Branch B and drops it directly into the cleaner, more concise logic flow of Branch A.
It splices the DNA of the two approaches.
It does. And this new hybrid trajectory evaluates the translocated evidence and successfully concludes that the original label is Custard Records. It scores a perfect 1.0.
And the beauty is, neither branch could have solved the problem alone through further autoregressive expansion.
No, they were totally trapped in local minima inside their entropy shells.
But by evaluating them densely with the backward search and recombining them with the forward search, the system constructed a path to the correct answer that just didn't exist in the original generation phase.
which is amazing. So let's see how this actually performs in the trenches. Because the theory is elegant, but post-training an agent requires serious stability.
Oh, definitely.
The researchers ran post-training experiments on logical and multi-hop reasoning tasks. For logical puzzles, they used the Knights and Knaves dataset with Gemma 3.1 Beat.
Right.
Standard GRPO and MaxRL completely flatlined. The training curves were basically horizontal because the problems were too hard for the base model to just randomly stumble onto the correct answer and receive a reward signal.
BES, however, steadily improved the validation accuracy throughout training.
Wow.
Yeah, because it was recombining partial logic strings, it successfully synthesized effective training samples where the standard reinforcement learning algorithms just starved from a lack of signal.
That makes sense.
And the results on the music dataset using Llama 3.2 3B Instruct are even more revealing about the flaws of current methods. They set up an agentic loop where the model could actively search Wikipedia before answering.
Okay, so if standard GRPO is starved for signal in that environment, I'd assume it starts optimizing for weird behaviors.
Oh, it did. Standard GRPO actively degraded the base model's accuracy. It dropped it from 4.0% down to 2.1%.
Wait, really? It got worse.
Yes. It's a textbook example of reward hacking. The search space for navigating Wikipedia is vast, and the terminal rewards are sparse.
Right.
The GRPO model quickly learned that exploring Wikipedia usually resulted in a 0 anyway, so it was more computationally efficient to just skip the search actions entirely and blindly guess the answer.
Oh, man. So it maximized its reward efficiency by doing less work, which just utterly tanked its real-world accuracy.
Yeah, exactly.
And if standard GRPO reward hacks by skipping the search, I'd assume tree GRPO struggles with the exact same blind spots since it relies on the same terminal reward.
It does. Tree GRPO barely moved the needle, achieving a 3.9% accuracy, which is essentially indistinguishable from the base model. But applying BES on top of GRPO boosted accuracy up to 7.0%. Furthermore, the agents trained with BES generated significantly more valid search actions.
So they didn't reward hack.
No, they actually learned to execute the complex multi-hop Wikipedia searches because the backward search tree rewarded them for finding the intermediate pieces of the puzzle.
That's incredible. So that covers post-training, but test time compute is where the massive money is being spent right now.
Oh, for sure.
They tested BES at inference using GPT-5 on incredibly difficult open problem-solving benchmarks. Specifically, mathematical optimization tasks like circle packing in squares and rectangles and the Habron convex problem.
And BES outperformed existing state-of-the-art open-source frameworks like OpenEvolve, GPA, and ShinkaEvolve.
Right.
It achieved higher top objective scores, and more importantly, it demonstrated much lower variance across runs.
And lower variance means the search is far more stable. You aren't just praying for a lucky random seed.
Exactly. The evolutionary process consistently converges on high-quality solutions.
But this brings up the most obvious point of skepticism.
Which is?
Running a forward evolutionary search like constantly evaluating pairs of parents, prompting semantic compilations while simultaneously running a recursive, backward LLM-judged goal tree sounds like an absolute computational nightmare.
Yeah, that's fair.
Is the wall clock time or the API budget going to bankrupt researchers trying to deploy this?
The compute cost is definitely the immediate concern for any ML engineer, but the cost analysis in the paper totally diffuses it.
Okay, let's hear the numbers.
Let's examine the wall clock time for the 3B post-training experiment. Standard GRPO was fast, taking 64 seconds per step.
But as we established, it was computationally useless because it learned to reward hack.
Exactly. Now, tree GRPO, which is the current industry standard for this kind of search agent post-training, took 240 seconds per step.
Okay, and what was the time for BES?
309 seconds.
Wait, that is less than a 30% time overhead compared to tree search.
Exactly, a 28.7% overhead. You're paying a very small time penalty for massive nonlinear performance gains and total resistance to the reward hacking that plagues standard methods.
That's wild. And what about the API costs for the GPT-5 inference experiments?
Also entirely manageable. The average cost for a complete BES generation was $18.06 compared to $13 for ShinkaEvolve.
So you are paying, what, a $5 premium for a significantly more robust test time scaling mechanism?
Right. And the reason the costs don't spiral out of control is because the backward search acts as a brutal pruning mechanism.
Of course.
By evaluating subgoals, the system aggressively identifies and kills off doomed trajectories early. You aren't wasting thousands of tokens expanding a branch that made a fatal logic error 10 steps ago.
That makes perfect sense. So what bidirectional evolutionary search fundamentally proves is that self-improving LLMs and agentic systems do not have to be trapped by their own autoregressive probability distribution.
Right. We can break out of the entropy shell.
Yeah. By introducing biological recombination to cross-pollinate ideas and dense sub-goal tracking to reward partial progress, we can navigate vast solution spaces that are just mathematically unreachable by best of n or tree search methods.
It completely shifts the entire paradigm of inference scaling. We are moving from a brute force, generate and verify approach to a much more sophisticated decompose, evolve, and synthesize approach. It treats self-improvement as a structured evolutionary search problem, borrowing literally the most powerful mechanism nature has for escaping local minima.
It really makes you wonder about the logical extreme of this architecture. I want to leave you with a fascinating implication to mull over.
Oh.
If BES proves that LLMs can escape their own entropy shells by crossing over reasoning paths like genetic material, what happens when we let entirely different base models cross over their reasoning traces?
Wait, you are suggesting an interspecies crossover?
Think about it. Could you use a BES framework to splice a highly creative, slightly unhinged open-source 8B model's trajectory with a rigidly logical, closed-source frontier model's trajectory?
Oh, wow.
Could you literally breed entirely new, alien reasoning structures that neither model family could ever produce on its own? We are talking about hybrid vigor for latent space reasoning.
The framework absolutely supports it. I mean, the evolution operators are completely model agnostic.
Yeah.
As long as the trajectories share a semantic space like raw text or Python code, you could absolutely cross-pollinate the intuitions of vastly different architectures to solve problems neither could tackle independently.
It's a wild frontier. So for those of you grinding away building the next generation of reasoning agents, I highly encourage you to check out the open source code linked in the paper at the Embodied Minds Lab GitHub repository.
Definitely go take a look.
Clone it, run it, and see what kind of mutant trajectories you can breed in your own ML pipelines. Keep experimenting, keep pushing the boundaries, and we will catch you on the next episode of AI Paper Slop.